Let's look at a few difficult examples of differentiation, and this time we're basically, again, just using the same power rule, but with some variations. So we differentiated something really easy in the previous video, which was just x squared. In this video, we're going to be differentiating something a little bit more difficult than that. And the first example that we have is basically differentiating 2x squared. So what we have is we have this thing, which is 2x squared, and we're supposed to differentiate it. Now, so if I just write my differential over here, this is going to be this thing, okay? This is what we're differentiating. Now, the thing is, whenever you have a constant, so this 2 is a constant. Whenever you have a constant term, okay, there are two types of terms. There are constant terms, and then there are variables. All sorts of variables are letters, A, B, C, D, E, F, G, H, I, to Y, X, and Z. But all sorts of numbers, that's what we call our constants. And so whenever you're differentiating and you have a constant, what you can do is you can basically pop that constant outside of the differential operator. So what I mean by that is just I can basically pick this 2 up, and I can take it over here, and I can go back to differentiating that x. Now this 2 is of course going to multiply to whatever the answer is going to be. So now we simply just need to differentiate x squared. So let's differentiate it. We are just going to get, so we can, how do we differentiate x squared? Well, this is the power rule. Whenever you have x raised to any power, the power rule is what you use. And so I'm basically just going to get 2x 2 minus 1, okay, and then this is going to be multiplied with that 2. So what am I going to get? Well, my entire answer is just going to be 4x, right? Okay, so let's go ahead and try out the second example. So we have this thing over here, and what I would suggest over here is to, well, first separate the variable from this fraction over here. Do that. Whenever you have a variable being stuck to some fraction or something like that, just try and separate out the variable. So that's what we're going to try and do. So another way of writing this would to just write it as 1 by 2 multiplied with under root x. Now this looks way neater. And now what I can do is I can basically convert this surd. I have a surd over here, right? This guy is a surd. This square root is a surd. I can convert this to a power, so that would just something that would just look like 1 by 2 x raised to the power 1 by 2. So what I did is I just first separated my variable, and then I just converted the surd to power, because I can apply a power rule on a power. I cannot apply power rule on a surd. So what I'm going to do now is I'm just going to apply my differentiation over here, which is this thing. And again, we have a constant. 1 by 2 is a constant term, so we're just going to take that outside of the differentiation operator. And what that is going to look like is basically, I'm trying to grab this entire thing. Okay, it's not working. But anyways, I can just basically pop all of this out. So now we're just supposed to be differentiating this x to the power 1 by 2. And that's fairly easy. So what we're going to get is this is going to be 1 by 2 multiplied with 1 by 2 times x, and we're going to subtract 1 from the power. So we're simply just going to get 1 by 4 x raised to the power minus 1 by 2. Okay, this is our final answer. Now let's try out our next example and sort of have something going on like this. So it's a cube root and an x squared. So what I can do is, well, I can first convert the cube root into a power. So that would just be something like this, where I have the surd converted into a power. And then what I can do is I have a power over here. I have a power over here. I can sort of multiply these two. And so this is just going to be this thing. And now what I can do is I can just differentiate this. So I would just differentiate this thing. And now my answer is going to be 2 by 3 x 2 by 3 minus 1. And you can simplify this, see what the answer is going to be. But the point is, see, in all of these examples, we're just trying to first simplify it algebraically and then differentiate. And this is what you want to be doing with your actual problems. You want to first algebraically manipulate them to make them differentiation ready, and then go ahead and actually apply the power rule or anything. So we're going to go, and we are going to try our fourth example over here, which is 8 over 3 x squared. And then again, this could be something like this. This could be some equation for y. So maybe you are given this thing as y equals 8 by 3x squared, and then they asked you what's the gradient of this curve, and so or the gradient of this line. And so what you would do is you would basically apply the differentiation operator on both sides. So it would basically be something sort of like this. So it would be d by dx. It's going to be this thing, and then you're going to apply the differentiation operator over here. Now remember, you can't do anything with that y, right? Because the only thing you're going to get is this thing. You're not going to apply any power rule or anything to that y. You can only apply power rule or something to terms that have x. Why? Because you're differentiating with respect to x. So if you have maybe something like this, like let's say you have dt by dx, then you can't do anything with that t. Your answer is just straight up going to be dt over dx. You can't do anything with this t. You can't apply power rule on it or anything. Why? Because it's this thing is an x, and it can only differentiate things which contain an x. So over here, if we go back, what we have is we can sort of have our operator as d by dx, and we had this thing. And I'm going to try and simplify it a little bit. So we had this thing over here, and I'm going to try and simplify it. The first thing I would do is I would basically try and separate that x squared. And one way I could do that is I could basically write the fraction like so. And then what I would want to do is I would want to bring this x squared into the numerator. That is the best version in which you can sort of differentiate your algebraic expression and find the answer. So what I'm going to do is whenever you have an x squared in the fraction, you want to bring it into the denominator, into the numerator. And so this is just going to be x minus 2. So what I did over here is I just had sort of a fraction like this, and I just took it to the numerator. And whenever you take a variable into the numerator, the power becomes negative. So if I have 1 by x and I take the x to the numerator, it'll just be x minus 1. If I have 1 over x minus 2 and I take it to the numerator, it just becomes x to the power 2. So the power just gets multiplied with a negative 1, you can say. So what I'm going to have over here is I'm just going to have this thing. This is going to be 8 by x multiplied by x raised to the power minus 2. And so my answer is just going to be 8 by 3, x raised to the power minus 2. Now I can sort of see that, okay, I have a constant over here, and then this thing is actually what I can differentiate. So what I'm going to do is I'm going to basically pop this constant outside, and I'm going to work on that x raised to the power minus 2. So I'm basically getting dy by dx equals 8 by 3, and then I have my differentiation operator over here, and I have x minus 2. And so now we can apply the power rule on this thing. And so I'm not going to write all of this, I'm just going to write the answer. It's just going to be 8 by 3 minus 2x minus 3. And then you can multiply this and get your answer. So what we're going to now be doing is we're going to go over this last problem, but I want to talk about these function notations that you can also see when you're differentiating. So just for example, let's say if I have this 4 over cube root x, one way you can see this is you can see this as y equals to this entire thing. Another way you can sort of see it as f of x equals this entire thing. And so in this case, what do you do? Do you write f of x df of x by dx? Is that what you do? Well, that's not what you do. So with function notations, it's a little bit different. And what you do is when you differentiate, you just sort of put, if this is my f of x, what I sort of do is, so this would be equivalent to y. And then what I do when I differentiate this is I just put a dash over here on the top of f, so that just means f prime. F prime basically means the derivative dy by dx. So what I'm going to do over here is I'm just going to differentiate this, but I'm not going to put a dx underneath this fx. So I'm just going to have my f prime of x over here, and then I'm just going to differentiate this as well. I'm not going to put this in an operator this time, because it's different notations. With functions, we don't really do this. We use this fraction notation sort of when we're dealing with y's and x's, not with f of x and x. So what I'm going to do is I'm just going to simply differentiate this, and over here on the side I can sort of imagine that, okay, I have my d by dx, and inside of it I sort of have this fraction 4 over cube root of x, and I can sort of do this on the side for my own sort of problem solving. And so what I would do is I would again first try and liberate that x from this fraction. And one way of doing that is, well, first of all, what I can do is I can sort of just change that cube root into a fraction. And then what I can do is I can sort of take this to the numerator, because I'm trying to get it out of a fraction. Then I'll just get 4x negative 1 by 3. And then what I can see is that this thing is a constant. That thing is x with a power, so I can differentiate that. So I'll just bring this 4 outside. It's going to be over here. And then all I'm going to have left is this x raised to the power 1 by 3. And then I can sort of differentiate this. So it's just going to be 4 multiplied with minus 1 by 3x, and then subtract 1 from the power. And then whatever this solves out to, that's going to be your answer. So I can just go ahead and plug that answer in here. I'm not going to completely solve this out, but you can go ahead and do that. So this is going to be this thing. So ideally, what do you want to do? Well, whenever you have your constants and you're applying differentiation, the constants can go out of this differential operator. Another thing that you want to do is when you have sort of these complex, tricky looking integrals, what you want to do is you first want to sort of isolate the x, and then what you want to do is you want to sort of turn them into a power form. Like if they're into a surd, it would be highly recommended to turn it into some power n, x raised to the power n, some power whatever. So if this is a square root, then the power would be 1 by 2. So just, talking about this, the simple concept of sort of making these guys, all of these guys, differentiation ready first, doing some algebraic manipulations on them to get them into a form on which you can then apply the power rule. Okay, and then this function notation over here, of course, this is how we write dy by dx when we're dealing with functions, this f prime. And again, this also tells you the gradient. It's the same thing. It's just written differently, but it's the same thing.